In trying to find global extrema, okay, global maximums or minimums, when we were working with single variable functions, we would find the critical points, and then we would compare the values at those critical points to the values at the endpoints of an interval. And that would give us an indication of what the global maximum is and then the global minimum is. Now, in a multivariable setting, we need to think about the interior and the exterior of a domain, or the boundary, of a domain. So we're going to let R be a closed subset of the domain of F, and global maximums and minimums of F can occur both in the interior of a domain and on the boundary. Now, in one dimension, the boundary of a domain was just the endpoints. But now I'm going to have some maybe set R. Okay, and so those global maximums and minimums, they could occur on the interior or they could occur on the boundary. And I'm going to have to test both. So if we want to find global maximums or minimums, okay, if I want to find the absolute maximum or absolute minimum values of f of x, y on a region R, okay, I need to locate interior critical points. And then I need to find the possible extreme values of f on the boundary of R. Okay, so I need to find the critical points on the inside, then possible extreme values of f on the boundary of R. Okay, I'm going to do that by parameterizing the boundary and turning this into a single variable problem. We'll see how that works in the examples. And then finally, I'm going to compare the values of f at the points found on the interior or on the boundary. And that's going to be my method. So let's look at some examples. Okay, let's find the absolute maximum and minimum values of the function f of xy equals 2 minus x squared minus xy on the rectangle that's defined where x is between 0 and 1 and y is between 0 and 2. So you'll see I've kind of drawn the rectangle for us. Okay, x is going to be between 0 and 1, y is going to be between 0 and 2. And I want to locate a maximum and minimum values, okay, inside that rectangle or possibly on the boundary. Well, the first thing I'm going to do is find critical points. So I'm going to find the gradient of f. The gradient of f in this case, if I take the derivative with respect to x, it's going to be minus 2x minus y. And then the derivative with respect to y is going to just be negative x. And I'm going to set that equal to the 0 vector. Okay? Well, the first thing that tells me is that looking at this partial derivative, that x is going to have to be 0. Well, once x is 0, when I look at this partial derivative, that tells me that y is going to have to be 0. Okay, so 0, 0 in this case is the only critical point. Well, I don't need to do the next step, but I do want to classify that critical point just for the practice. Okay, so this is actually not necessary to find global maximums and minimums, but I'm going to do it anyway just for the practice. And that is, I'm going to find that Hessian matrix for f. So the Hessian matrix, okay, so that's the derivative of the x derivative with respect to x. So that's going to give me negative 2. Okay, the derivative of the y derivative with respect to x, that's a negative 1. And then the derivative of the y derivative with respect to x is going to give me a negative 1. And then the derivative of the y derivative with respect to y is going to give me a 0. Okay, and I'm going to find the Hessian there, and then the determinant of the Hessian. Well, that's going to equal, let's see, negative 2 times 0 is 0, and then minus negative 1 squared. So negative 1, it's less than 0. So this is neither. It's not a maximum or minimum. So that point is not going to be a local maximum or minimum. Okay. So instead, we're going to want to compare the value of f at that point, okay, to the value of f on the boundary. Okay. So let's evaluate that point. Let's make sure we understand here that f of 0, 0, okay, is going to be 2. We're going to use that for comparison. Okay, now what I would like to do is parameterize the boundary. Okay, so here I would like to essentially make this a one-dimensional problem. Okay, so what I'm going to do is I'm going to look at each edge of the boundary. So I'm going to start with the first edge 1. Okay, and so what I'm going to do is along there, I'm going to let x be t along that edge, and then y has to be 0. Okay, so I'm parameterizing the curve that's labeled by 1 there. Okay, x is t, y is 0. Okay, then when I do that, I'm going to find f of t 0, so f along that boundary. Okay, so that's going to be 2 minus t squared. Okay, here, by the way, I should point out that x is going to be between 0 and 1 in this case. So t in this case is going to be between 0 and 1. So f of t 0 is 2 minus t squared. That's a single variable function. Okay, so I just need to find the maximum and minimum of that single variable function. Okay, the maximum on that interval, okay, is going to be at t equals 0. Clearly, it's largest when t equals 0. That's when f of 0, 0 equals 2. Oh, that was one of my, that was my critical point, actually. Okay, and then the minimum for that function is clearly going to happen at t equals 1. Okay, I could take derivatives, set it equal to 0, do all that, but it's just easier to just look at that function, and I'll see that the minimum is at t equals 1. Okay, that's where f of 1, 0 is equal to 1. Okay, so those are candidates for a possible maximum or minimum. Okay, let's look at boundary 2. This is interesting. So x in this case is 1, and then y I'm going to let be t. Okay, and then the idea is that t can be anywhere between 0 and 2. Okay, well, so I'm going to do f of 1t. So I'm going to plug those in. So I'm going to get 2 minus 1 is 1 minus 1 times t, which is t. So that's just the function 1 minus t. That's going to be easy to maximize. The maximum is going to be at t equals 0. Okay, that's where we have f of 0, 0 is equal to, at t equals 0, that's going to be f of 1, 0, which is 1 in this case. And then the minimum along that curve, that's going to be at t equals, let's see, t can go all the way to 2. So that's going to be where we get f of 1, 2, which is negative 1. Okay, those are candidates for the maximum and minimum. Okay, let's look at curve 3. Okay, that's where x I'm going to let be t. And then y in this case is going to be 2. So I look at this one, I'm going to get f of t and 2. And that's going to be 2 minus t squared minus, and then x times y is 2t. Okay, so that is the function that I want to find the maximum and minimum of. Okay, in this case, t is going to be between 0 and 1. Okay, I will notice that the derivative of this function f prime of t is going to be minus 2t minus 1. And when I set that equal to 0, that's going to give me t is negative 1. And that's actually not in the interval from 0 to 1, so we don't have to worry about that one. Okay, so we're just going to look at the endpoints. So we're going to maximize this. We're going to maximize again at t equals 0. Okay, so we're going to do f of 0, 2. F of 0, 2 in this case is going to be 2. Okay, and then we're going to do the minimum when that happens. The minimum is going to happen when t equals 1. Okay, that's going to give me f of 1, 2, which we've already found is going to be negative 1. Okay, so there we found some more candidates. And then finally, looking at this fourth curve, the fourth curve occurs when x is equal to 0 and then y is equal to t. Here we have that our t is going to be between 0 and 2. Okay, so we get that f of 0t, so x is 0, f of 0t, well, that equals just 2. Oh, it's constant. Okay, so we have a maximum that occurs at f of 0t is equal to 2. Okay, so what are the results of parameterizing the boundary? Okay, so what are the results? We're going to get a global minimum, which is f of 1, 2, which was negative 1. So if we look at all these points that were candidates for maximums and minimums, okay, it's smallest at 1, 2, so that's the global minimum. Okay, and then we're going to get a global maximum. Global maximum happens when you get the value of 2. So when do you get the value of 2? Well, anytime you plug in x equals 0, you get 2. So f of 0 and any y is going to give you 2. Okay, so there's actually infinite points here that give you a global maximum. Okay, and so on that rectangle, we have now found the global maximum and minimum. Okay, so these problems where you have to parameterize the boundary, they can be quite lengthy. Okay, so let's look at another function. Okay, we're going to find the maximum minimum value of a function f of xy is equal to x squared plus y squared minus x minus y plus 1 on a triangular region. Okay, so first we need to find the interior points. So let's find the gradient of f. Okay, the gradient of f is going to be, in this case, 2x minus 1 and 2y minus 1. We're going to set that equal to 0, 0. And then if we solve, we need to get x being a half and y being a half. Okay, now this critical point is truly in the interior. Okay, x is a half, y is a half. So it's right here. Okay, if we have our triangle. Okay, so here we have an interior point, and then let's figure out what is f of 1/2, 1/2, just so that we have it for comparison. F of 1/2, 1/2. In fact, if we plug that in, we will get the value 1/2. Okay. Now, this next part is not necessary, but I'm going to classify just for practice. Okay, what kind of point is this? Okay, so I'm going to need to find the Hessian matrix for f. Okay, so the second derivative with respect to x is going to be 2. Take the derivative of x with respect to y, and I'm going to get 0. Take the derivative of y with respect to x, so I'm going to get 0. And then the second derivative with respect to y is 2. So I have that my determinant of my Hessian is positive. Okay, it's going to be 4. Okay, fxx is 2, so that's going to be positive. Okay, so this is going to give me a local minimum. Okay, using that criteria, this is going to give me a local minimum. Okay, now that I have that, I'm going to want to parameterize the boundary again. Okay, so here I want to parameterize the boundary. Okay, so we're going to do that. We're going to start with 1. Okay, so along that bottom, I'm going to let x be t, and then I'm going to let y be 0. Specifically, I'm going to look at t's between 0 and 2. Okay, so if I let x be t, then I'm going to get f of t 0 is in fact going to be t squared minus t plus 1. Okay, and when I look at this, I'm actually just going to look on the interior of these lines, make it a little bit easier on myself here. Okay, so there's my single variable function. I'm going to do f prime of t is going to be 2t minus 1. That tells me that t needs to be a half. Okay, so f of 1/2, 0, that point is going to be 3/4. Okay, so I just found points on the interior of that boundary curve 1. Okay, and the very end, I'm going to go back and I'm going to check these 3 vertices. Okay, so do I get the whole boundary? Okay, so when I do when I do the boundary curve 2, that's where x is going to be 0 and y is going to be t. 0 is going to be less than or equal to t is less than or equal to 2. Okay, so here I'm going to get f of 0t. That, when I plug it in, is going to be t squared minus t plus 1. Oh, that's interesting. That's basically the same thing, right? I could take the derivative. It's going to give me 2t minus 1. Tells me t is a half. And so, in fact, f of 0 and 1/2, that's going to give me, again, 3/4 when I plug that in. Okay, so now here comes the last one. It's a little bit more difficult. Okay, I want to parameterize the boundary 3. Here I'm going to let x be t. Then y, if I'm looking at the line, has to be 2 minus t. Okay, because that's the line 2 minus x. Again, t is between 0 and 2. So I'm going to get f of t, 2 minus t. Plug that in. I'm going to get t squared plus 2 minus t squared. So that's x squared plus y squared. Okay. Minus t minus 2 minus t, and then plus 1. Okay, so I need to kind of simplify that just a little bit, see what I can get here. I'm going to get a t squared plus 4 minus 4t, and then plus t squared. It's going to give me a minus t minus 2 plus t plus 1. Okay, so let's see what we get here. So I notice that this t is going to cancel with that t. Okay, and I'm going to get 2t squared. Let's see. Minus 4t. And then plus 4 minus 2. So that gives me 2 plus 1, which is plus 3. Okay. So there is my single variable function. So now I'm going to take the derivative of that to find f prime of t. F prime of t in this case is going to be 4t minus 4. Okay, set that equal to 0. And that's going to tell me that t is going to be 1. Okay, so in this sense, I need to check the point 1, 1. Okay, so f of 1, 1, what's that going to be? So let's look back at what the function is. F of 1, 1, so I'm going to get 1 plus 1, minus 1, minus 1. Okay, that gives me 0 plus 1. So f of 1, 1 in this case is going to be 1. Okay. So I have a few more things I've got to check here. Okay, so now I've got to check the endpoints. Okay, what's going on at the endpoints of the triangle? So if I plug in 0, 0 to my function, okay, I'm going to get x squared plus y squared minus x minus y. All that stuff is 0, so I'm going to get 1. Okay, I'm going to plug in f of 2, 0. F of 2, 0, well, I'm going to look at this function. Okay, I'm going to get 2 squared minus 2 plus 1. So that's going to give me 3. Similarly, f of 0, 2 is going to give me 3. Okay, and now I've checked all of these points. Okay, so what I need to do is look at all of the possible points, okay, that I was looking at. So first, I'm looking at a half. Okay, that's a possible point for the minimum. Okay, then I've got 3/4. Okay, those are bigger than a half. Then I've got 1. And then finally, I've got 3 and 3. Okay, so that tells me I have a global minimum. The global minimum in this case is f of 1/2, 1/2. That's going to equal 1/2. And then the global maximum, there are 2 of them. Okay, that's where we get at 2, 0 and 0, 2. Those are both going to be 3. Okay. So you can see this is kind of a long process that I've used. Okay, so I basically found the local maximum or minimum. In this case, it was a local minimum, okay, on the interior. And then I parameterized the boundary. I parameterized each of the boundaries, 1, 2, and 3. And I just looked for critical points on the interiors of 1, 2, and 3. And then I finally went back and I checked all of the vertices of the triangle. Okay, and then that finally gave me the global minimum and maximum. Okay, let's go to one more example that will be a little bit more straightforward, a little bit simpler. Okay, we're actually going to find the global maximum and minimum values of the same function, x squared plus y squared minus x minus y plus 1. But now I'm going to look at within the circle, x squared plus y squared is less than or equal to 1. So here I've got essentially the unit circle, and I'm curious about inside the unit circle, okay, what are the maximum and minimum values? Okay, so recall that at a half, okay, I had my critical point. So I'm going to just recall that I have a critical point where f of 1/2 is equal to a half. So that's my critical point. It's the same as the previous example, but now I want to parameterize the boundary. So I'm going to parameterize the boundary, and that's going to be x squared plus y squared equal 1. Okay, and you'll recall we can do that by letting x be cosine t. Okay, that's r cosine t. R in this case is 1, and y is equal to sine t. So that's going to parameterize our circle. And so instead, we're going to do f of t in this case. So f of t is really f of cosine t and sine t. Okay, we're going to plug that in. That's going to be cosine squared t plus sine squared t minus cosine t minus sine t plus 1. And so cosine squared plus sine squared is 1. So 1 plus 1 is 2. So it's going to be 2 minus cosine t minus sine t. That's going to be my function on the boundary. So by parameterizing the boundary, I now have a new function f of t, okay, that tells me what's going on the boundary. And I want to maximize that function. So I'm going to take the derivative, or minimize that function. So I'm going to take the derivative. Okay, the derivative of minus cosine t is actually going to be sine t. The derivative of sine t is going to be cosine t. The derivative of 2 there was 0. Set it equal to 0. So I'm looking for points where sine t is equal to cosine t. Okay, well, there's only 2 points on the circle where sine t is equal to cosine t. Okay, that's going to be when t equals pi over 4. Okay, that's where sine is 1 over square root of 2 and cosine is 1 over square root of 2. And then also at 5 pi over 4. Okay, that's where both sine and cosine are negative 1 over square root of 2. Now, of course, there are other t values that would make sine and cosine equal, but I only need to look between 0 and 2 pi because I've covered the entire circle between 0 and 2 pi. So here I'm assuming that t is between 0 and 2 pi. Okay, so I really just need to figure out, okay, what's f of pi over 4 in this case? Okay, so another way to think about that is f of cosine t, which is 1 over square root of 2, and sine t, which is 1 over square root of 2. Okay, so I'm going to plug those in. Okay, that's going to be 2 minus 1 over square root of 2 minus 1 over square root of 2. Okay, if we simplify that, that's 2 minus the square root of 2. Okay, so now I'm going to do f of 5 pi over 4. That's actually going to be f of negative 1 over square root of 2, negative 1 over square root of 2. Plug that in, that's going to be 2 plus 1 over square root of 2 plus 1 over square root of 2. So in fact, this is 2 plus the square root of 2. Okay, so now I've got my candidates. Okay, my candidates are the half here, 2 minus the square root of 2, 2 plus the square root of 2. Those are my candidates for maximums and minimums. Okay, so let's figure out which one is the smallest. So here we're going to find the global minimum. The global minimum in this case is actually at a half. That's actually the smallest one. 2 minus the square root of 2 is 2 minus about 1.4. So this one here is about 0.6, okay, ish. Okay, so it's bigger than a half. So that's my global minimum is actually a half. And then the global maximum That's clearly going to be 2 plus square root of 2. So that's f of negative 1 over square root of 2, negative 1 over square root of 2. So that's going to be 2 plus the square root of 2. Okay, so that's interesting. Okay, if I come back up over here, right, this one where the minimum was. Okay, the maximum is actually here. So that ends up being the maximum. And so this is just another example of how to find global maximum and minimums. Okay, when we're looking on a closed domain. Okay, so we're looking inside of this closed disk, and we have to look at both the interior and the boundary.